So we know that we can actually use the modified Arrhenius equation to figure out the effect that temperature will have on a rate constant. We can calculate our new rate constant based upon temperature change. We also now have a way to figure out that activation energy, the hurdle, as it were, to actually get our bonds to break and our new ones to form. And we've actually seen this before, and it's good to kind of go back and review. And so I want to make sure we're talking the same language and got all the pieces we need to be able to kind of talk about when we say activation energy and kind of the progress of a reaction, what that is that we are referencing to. And so today for your notes, we're just looking at a couple of graphs. Make sure you got all the terminology, a couple of different ways we can start to navigate these graphs, but we have seen these before in terms of the change of the energy of our products versus our reactants. And that is our change in internal heat energy, or our enthalpy, delta H, if you remember from our college chem days. So just as a reminder, we got kind of two basic types of reactions that we have. We got endothermic, where our heat energy is being absorbed, and exothermic, where heat energy is being released. We're thinking about our products versus our reactants. For these two, we would see two very distinct differences. You'll notice for our endothermic, our final products, which are at the end of the reaction, typically across our x-axis here, we'd say we've got our reaction progress as opposed to time, nitpicky stuff. Anyway, so products here at the end. For an endothermic reaction, our products have more heat or internal energy than we actually started with. And so we've got a higher value than our reactants, which are back at the left. That's what we started with. For an exothermic, we say that we've actually lost heat energy, that it's left the system. And so our final products are lower in terms of their final energy than what you started with. So just a couple of things to highlight here. So our energy of reactants are always what we're starting with. Our energy of the products are what we're always kind of going to end with. And the difference between those, if you remember, is our change in enthalpy, or delta H of the reaction. And so if we took a number, a larger number, our final minus our initial, we get the change, right? The delta. So if we take a larger mathematical value minus a smaller number, we end up with a positive delta H. And that was a big piece we stressed last year. If we had a positive delta H value, that meant it was endothermic. It was absorbing energy, and you were ending up with more final heat energy than what you started with. For an exothermic process, you've got a smaller energy value minus a larger, so a small number biggest of minus a larger value means that we have a negative delta H, or an exothermic reaction. Just remembering what our sign connotations mean for us in terms of our changes in our energy. Cool, and then we got the hurdle. Oh, so kind of the big piece here, the hurdle, or the hump we got to get over here, is our activation energy. It's also where we're making and breaking the bonds. And sometimes we refer to that as our transition state. That's where we're actually changing. That's where we're physically changing from reactants to products. We're breaking and making bonds simultaneously. And you'll notice that it's a lot of energy. It takes a lot of energy to have our bonds break and form all at the same time. So we always kind of have this activation energy. And so we can start to describe that in a couple of different ways. If we're looking at how large that initial, if we're going from left to right, that initial difference in energy is, we set that as EA forward, or activation moving forward in the reaction. If we wanted to solve for that, mathematically what we would do is we would take the energy of our transition and we would subtract by the energy of our reactants. And so the difference in those energies gives us how much energy we need to put in to get over that hurdle to get to our products. If we were going to go backwards the other way, we would say that this is our EA reverse. And it's kind of the same deal. If we want to know the activation energy in reverse, we would take that activation, or that energy of the transition state, minus the energy of our products. And so that would give us our activation energy going back the other way. And the reason why we would care about that, because if you look at your graph, the difference in those energies gives you your delta H of the reaction again. And so if you wanted to, you could solve for a whole myriad of different things based upon what energies you've been given and kind of what values you've got for your reactants, your products, your transition states, or your activation energies, or your delta H. And so we're kind of taking all these pieces and we're pulling them back together to be able to describe what is happening during the changes in our reaction and the energies that it requires for this to occur. We're going to dig more into the transition states, what actually happens in that kind of nebulous region in between reactants and products. We haven't spent a lot of time talking about that, but that's kind of where we're heading to next in terms of our different rates of reactions and our kinetics moving forward.